Welcome to Graph Homomorphisms and Universal Algebra session number 7. Last time we have seen that if we have two structures, A and B, and every relation of B is primitively positively definable in A, then we can reduce the constraint satisfaction problem for B to the constraint satisfaction problem for A. However, note that in order for this method to work, we need that A and B have the same domain, or at least the same domain size. We would like to have a method that also works for structures that have different domain sizes. And the method we have for this, it's a very strong method. It's stronger than primitive positive definitions from last time. It's called primitive positive interpretations. This method will precisely allow to compare structures of different domain sizes, and this is the topic of today's video session.
Primitive positive interpretations might look very technical if you see them for the first time. So we better start with an example. It is an example that you all know, namely the interpretation of the field of rational numbers over the integers. Basically, we follow one way how to formally introduce the rationals. What is a rational number? We write them as x over y. Formally, the elements of Q are equivalence classes of ordered pairs, xy, of integers, such that y is not 0. I may even assume that y is at least 1. Two such pairs are equivalent if they represent the same rational number, which can be expressed using multiplication over the integers. A rational number x1 over y1 equals a rational number x2 over y2 if and only if x1 times y2 equals x2 times y1. With addition and multiplication, we can express how to add two rational numbers, x1 over y1 and x2 over y2. The result is x3 over y3 if and only if the following equation is satisfied in the integers between the coordinates. This equation is familiar to you if you multiply both sides of the equation with y1 times y2 times y3. Finally, we can also express how to multiply two rational numbers. Note that all the conditions that you see on the right can be expressed by primitive positive formulas over the integers with addition and multiplication. This is obvious for the formulas for equivalence, addition and multiplication. For the condition that y is at least 1, there is a little trick involved that you find in the script. We now define primitive positive interpretations formally. Suppose that we have a relational tau structure A and a relational sigma structure B. The definition would also be possible for not necessarily relational structures, but it would be more to write, so today I focus on relational structures only. A primitive positive interpretation of B in A is defined as follows. It has a dimension D. In our example of an interpretation of Q in Z, this was 2, since each element of Q was simulated, so to say, by two tuples of integers. Then there must be a primitive positive formula with D free variables in the signature of A that defines in A those D tuples that we want to use in order to simulate the elements of B. This formula is called the domain formula. In our example, this was the formula that forced the denominator to be at least 1. We also need for each atomic sigma formula phi with k free variables a primitive positive tau formula, phi sub I for interpretation, which has d times k variables. The reason is that each element of B is simulated by d elements of A. So if we have k variables over B, we need d times k variables over A. These formulas are called defining formulas. In our example, we had two ternary relations, one for addition over Q and one for multiplication over Q, and the dimension was 2. And indeed, the formulas that I underlined in green in the example had d times k equals 6 free variables. Finally, for our interpretation, we need a surjective map from those d-tuples that satisfy the domain formula to the elements of B. It maps the d-tuples to the elements they simulate. I require it to be surjective because every element of B needs to be simulated. On the other hand, this map need not be injective. In our example, for example, the same rational number might have different representations, x over y. And all of these representations would be mapped to x over y. This map is also called the coordinate map. And sometimes the interpretation itself is identified with the coordinate map. So we write I instead of h. So this is what constitutes an interpretation. But of course I still need some requirement to explain how all these things relate to B, to our structure B. The requirement says that for all atomic formulas phi over the signature of B, and for all elements A11 up to AKD, the structure B satisfies phi on the k-tuple that you obtain by applying the coordinate map to A11 up to A1D, then to A21 up to A2D, and so on, if and only if A satisfies the interpreting formula for phi on the elements A11 up to AKD. This says in particular that a tuple is in a certain relation of B if and only if the interpretation says that there should be such a tuple. In our example about Q and the integers, this is precisely that the formulas I wrote down are correct definitions for addition and multiplication as we know it in Q. Let's have a look at another example. I will draw a certain graph G. In this graph, we have a primitively positively definable equivalence relation E. The equivalence classes are drawn by red bags. So E is primitively positively definable because two elements are equivalent if and only if they lie in the same triangle, in the same copy of K3 in G. And this can clearly be expressed by a primitive positive formula. Now, I claim that the graph K5, the clique with 5 vertices, has a primitive positive interpretation in this graph. The dimension of the interpretation is 1. The atomic formula x equals y in K5 has the defining formula E applied to x and y. And then the edge relation in K5 can be defined primitively positively from the edge relation in G. The idea is that we can obtain K5 by defining the edges on the equivalence classes of E. We basically contract the equivalence classes of E into single vertices and we obtain K5. The first thing that we prove about primitive positive interpretations is that they preserve the complexity of the constraint satisfaction problem. Exactly as in the case of primitive positive definability, we have that if a structure B has a primitive positive interpretation in a structure A, then the CSP of B can be reduced to the CSP of A in polynomial time. The proof is also very similar. We may view an input instance of CSP B as a primitive positive sentence phi. To answer whether B satisfies phi, we translate phi into a sentence over the signature of A. To do this, we simulate each variable y of phi by d new variables x1 up to xd. So if phi has n variables, we need d times n variables, which I call x11 up to xnd. Then we replace each conjunct of phi by the corresponding interpreting formula from the interpretation. Note that also in this step we introduce many new existentially quantified variables. In this way, we can obtain a primitive positive sentence which is true in A if and only if the original formula phi is true in B. Note that the new sentence can be computed from the old sentence in linear time. So altogether we obtain the polynomial time reduction. We now present an interesting application of primitive positive interpretations. We show that for every structure with a finite relational signature, there is another relational structure with a polynomial time equivalent CSP, which is binary, by which I mean that all relations have maximal arity 2. That is, there's a polynomial time reduction from the CSP of the original structure to the CSP of the new structure and vice versa. For finite structures, we may even find a digraph which has this property, but for our result we need several binary relations. To prove this, let M be the maximal arity of the relations of C. Our structure B has domain C to the M. For every relation R of arity K, we introduce a unary relation R' in B. Namely, the relation that contains all M tuples whose first K entries form a tuple in R. Note that this relation really has arity 1, even though it contains M tuples. But the reason is, of course, that the domain of B consists of M tuples. These unary relations are not enough for coding all the information about C. We also need some binary relations, but they are really simple. For all I and j, we have in B a binary relation Eij, which contains all pairs of M tuples such that the ith entry of the first tuple equals the jth entry of the second tuple. Note that if I equals j, we obtain an equivalence relation which states that two M tuples have the same ith entry. We claim that the structure B that we have just defined on the domain C to the M is primitively positively interpretable in C. This is actually quite clear from the definition. The interpretation has dimension M, the coordinate map is the identity, and all the definitions of the relations of B that we gave were already primitive positive. What is more interesting is that we can also interpret the original structure C primitively positively in B. Here we even have a one-dimensional interpretation. The coordinate map is simply the projection, so it projects each M tuple to their first entry. The atomic formula x equals y has the interpreting formula E11. To understand why, let's look at a small two-dimensional example. So I'm drawing the elements of B as a little grid. Note that the relation E11 is an equivalence relation on the domain of B, which states that two elements have the same first entry. So E11 holds on two elements of B if and only if the coordinate map sends them to the same element. So this is why E11 applied to xy is an interpreting formula for the atomic formula x equals y in C. Now we also need interpreting formulas for atomic formulas of the form relation symbol R applied to variables x1 up to xk. We need to use the unary relation R' that we have added to our structure B. And here we again use the relations Eij. We say there exists an element y of B which is in R' such that the first k entries of y are precisely x1 up to xk. Clearly, this is a primitive positive formula and it does the job. So we have primitive positive interpretations of B in C and of C in B. The previous lemma, actually it was a proposition, I'm sorry. That therefore implies that CSP B and CSP A can be reduced to each other in polynomial time. So the message is, in constraint satisfaction, the binary case is already as interesting as the general setting, which is nice since binary structures are easy to draw. Today's break is about a small real-life optimization problem. It's the challenge to find the highest point in Dresdner Heide. So this is a non-trivial task since you should know that there are so many trees in Dresdner Heide that you don't see the highest point. You might always choose the paths that lead upwards, but sometimes there are several paths that lead upwards, and you have to choose. Moreover, there are some local optima that are not global optima. Of course, you should not use Google to solve this task. My recommendation is, whenever you get stuck at a local optimum, you climb up a tree and you look for some higher point, and then you go into this direction. The winner of the challenge has to prove this by sending in a witnessing photo at the global maximum.
If we are given a structure and we would like to understand the computational complexity of the constraint satisfaction problem for this structure, we have seen already two methods. The first is that maybe our structure is homomorphically equivalent to another structure which we already know, which has an NP-hard CSP such as K3. In this case, the CSPs are the same, so we are done. There's nothing to be shown, our CSP is NP-hard. The second tool we have seen is primitive positive interpretations today. How about combining the two methods? It could be that our structure primitively positively interprets another structure, and this structure is homomorphically equivalent to K3. In this case, we also succeeded in proving NP-hardness of the CSP of the original structure. And this could be even iterated. It might be that we primitively positively interpret a structure B, which is homomorphically equivalent to a structure C, which primitively positively interprets a structure E, and so on. So in fact, we are interested in the class of all structures that you can obtain by either primitive positive interpretation or homomorphic equivalence or iteration. Surprisingly, this class of structures has very beautiful descriptions, and one we'll see today.
So let's introduce some terminology. Let C be a class of structures. All structures today are relational. I will write H of C for the class of all structures that are homomorphically equivalent to a structure from C. And I of C I will write for the class of all structures with a primitive positive interpretation in a structure from C. We are interested in the smallest class D that contains C and that is closed under applying the operator H and the operator I. A not so old result of Libor Bartow from Prague and Jakub Oberschall, who was at the time Libor's PhD student, and Michael Pinska from Vienna, states that this class can be described as first applying I and then applying H. There's no need to iterate. And this is just one of many equivalent descriptions of the class D that we'll see later on. One inclusion in the theorem is trivial. If we can obtain a structure by taking first I, then H, then we can also get the structure by taking I and H as many times as we want. For the reverse inclusion, first note that H of I of C contains C. This is because every structure PP interprets itself and every structure is homomorphically equivalent to itself. So this is clear. So it suffices to prove that the class H of I of C is closed under both H and I, because D is the smallest such class. Closure under H is easy, because homomorphic equivalence is an equivalence relation. So applying H twice is the same thing as applying it once. Closure under I can be split into two inclusions that we have to prove. The first is that we can swap first applying H and then I to first applying I and then H. And then we prove that applying I twice is the same thing as applying it once, as in the case of the operator H. And this will conclude the proof. To prove the inclusion that we have indicated in green, let A and B be structures that are homomorphically equivalent. And suppose that C has a d-dimensional primitive positive interpretation in B. We have to prove that there exists a primitive positive interpretation J of a structure D in A, such that C and D are homomorphically equivalent. That is, we have to close the following diagram drawn on the right. We can take for J the same interpreting formulas as in I, but we interpret them over the structure A instead of B. Note that this is possible since A and B are homomorphically equivalent, so in particular they have the same signature. Also, the interpretations I and J have the same dimension. Note that fixing all the interpreting formulas determines the structure D up to isomorphism. We have to prove that D is homomorphically equivalent to C. Let H1 be the homomorphism from A to B, and let H2 be the homomorphism from B to A. We can then write down explicitly what the homomorphisms between C and D are. We start with the homomorphism from D to C. Every element of D can be written in the form J applied to A1 up to AD. This element is then mapped to the value of the coordinate map of I applied to the image of A1 up to AD under H1. And G2 is defined symmetrically. It's an easy exercise that I leave to the audience to verify that these maps are indeed homomorphisms. The final piece in the proof is the verification that primitive positive interpretations compose. By this I mean that if C1 has a PP interpretation I1 in C2, and C2 has a PP interpretation I2 in C3, then there is also a PP interpretation of C1 directly in C3. In fact, there is a canonical way to compose the two interpretations to obtain an interpretation whose dimension is the product of the dimensions of I1 and I2. The coordinate map of I1 composed with I2 is the obvious composition of the coordinate maps of I1 and I2. So this shows that the operator I that takes a class C to all structures with a PP interpretation in C is idempotent, in the sense that it suffices to apply it once. If a structure B is homomorphically equivalent to a structure with a PP interpretation in A, then Bartow, Opperschall and Pinsker say that B has a PP construction in A. So PP definitions are subsumed by PP interpretations, which in turn are subsumed by PP constructions. So we have stronger and stronger tools to prove NP-hardness. PP constructions are the strongest. A lot of what we have done today can be summarized by the following. If a structure A can PP construct K3, then CSP of A is NP-hard. In 2017, Andrei Bulatov and Bulatov-Zhuk independently proved that if this hardness condition does not apply, and A is a finite structure, then in fact CSP A can be solved in polynomial time. Last time I was teaching this course, this was still a conjecture. In our course, we tried to cover as many basic concepts as possible that are involved in the proof of this fantastic result.
Noise you couldn't quite locate or explain. Couldn't quite locate or explain. Noise you couldn't quite locate. Noise you couldn't quite locate.